Alright, hello and welcome everybody to our first video in this CAD and design learning series. Today we're going to be talking about, well, this is our first lesson. So first we're going to go over the curriculum that we're going to be going through in these next few lessons. Now, introducing myself first, I'm Lucian. I am a designer on FRC Team 4795, the eSpots. And the aim of this curriculum is sort of just to give a little bit of insight into what I wish I had coming into this team on my first year. And that's basically just some context into how to do design, how to make CAD, and how to do practical design that can fulfill a task for robotics. And that's what we're going to be doing over the course of this curriculum. So the first part of, man, I really skipped over all of that there. Hold on. So the first part of our slideshow today is going to be a curriculum overview. Now, this curriculum is designed to teach elements of task-based mechanical design. If you take one thing away from this lesson, it's that mechanical design is task-based, right? When you're designing a thing that solves a problem, right? So in robotics, the problems are pretty self-evident, right? When the game is revealed, there's different ways to score points, and so scoring those points in those different ways, those are your tasks. But the first thing of any design, right, the first part of your design workflow is always going to be identifying your task, identifying your problem. So with a specific focus in student robotics applications, like I said before, student robotics gives you some pretty clear tasks to go over. So this course is going to cover three main topics, right? Each will eventually become relevant to the long-term goal of practical design ability. So first, we're going to be covering FRC and practical design. So FRC being the First Robotics Competition, FRC. So FRC and practical design, right, this is going to cover practical parts, mechanisms, machining techniques, and overall design philosophy that we're going to be using when we're designing for student-led robotics. Now, this is the main thing that I wish I'd had, because coming into robotics, I knew how to do CAD, but I did not know how to do design for robotics, and they're very different things. They're two very separate things. They're separate skills to learn, but if you have both skills, you can really do some really awesome things with design, right? So we're going to be covering practical parts to use, right? What parts we can buy and modify on our team, what mechanisms we can use, what machining techniques we can modify those parts with, and then overall design philosophy. So how do you build these things into a robot that can do game tasks, right? A robot that can play the game is the end goal. Then we're going to get oh man, I really screwed up there. Then we're going to get into CAD Basics using Onshape, right? So Onshape is the CAD software of choice for our team, and that's just because of its many online features as well as collaboration, and some really great file management, as well as intuitive CAD features. If all that sounds like garbage to you, don't worry, it sounds like garbage to me too. So yeah, we're going to cover creating parts, right? Downloading and modifying common off the shelf, or COTS, C-O-T-S, common off the shelf parts, and creating properly constrained mechanical assemblies. This is literally all we do for robotics CAD, right? We download and modify parts that we would be able to buy and machine, right? Downloading them and modifying them is the CAD equivalent of buying and machining them, that we would be able to do in real life, right? So, and then we also create properly constrained mechanical assemblies in order to incorporate these parts into a proper robot, right? And then lastly, we're going to combine units 1 and 2, doing task-oriented practical design projects. So that's using these practical design elements plus CAD, right, to create some designs that can solve a task. All right, so now let's get to Intro to FRC Design, right? Let's get started here. What does the design team do? So like I said before, here's this phrase, task-based again, right? So task-based mechanisms are comprised of parts and assemblies. So when you're creating CAD, right, you're going to create assembly designs in CAD, which are used as a blueprint for the robot's eventual construction. So the mechanical team will look at the CAD and they'll say, okay, this thing needs to have holes here, here, and here, right? So we'll do that on the drill press, and then we'll put it together with bolts, stuff like that. And then you're also going to be reviewing CAD designs in peer-led design reviews, and basically what that ensures is that your designs are good. Having good designs is very important because it saves you time and it saves you money. And then we're also going to be prototyping and iterating designs, right, which ensures that they can do the task. So a prototype is basically a physical version of your design, and prototypes are really just used to test specific things, like first of all, will it work at all? And second of all, like, will these specific things work? And if not, how can we change them so that they do work, right? And then you're going to create engineering drawings of parts that are used by the mechanical subteam when machining, right? So when mechanical subteam's machining, they're going to use the drawings that you make of the parts in order to use as a reference to machine those parts. Then you'll also assist electrical team with component and board layouts, right, in the robot CAD. That's something we haven't done as much, but it's something we're going to start to do more in the future. And that allows us to just have more fleshed out electrical systems on our robot. So overall, design team, basically we create the design for the robot, right? We start out by analyzing the task, then we go through the concepting phase, right? So we come up with some general concepts that could fulfill the task. Then after that, we're going to go ahead and create more fleshed out versions of those concepts using 2D paper sketches. And then after that, we'll decide on a concept to go with, and we'll create CAD of that concept. After we create CAD, we'll create a prototype, or no, first before we make a prototype, we'll do a design review in order to ensure that that CAD is good. And after we, make the edits brought up in the review, right, and the review will be with the whole team. After we make the edits brought up in the review, then we'll go ahead and make prototypes, test that, and once we have a satisfactory design, we'll build it and put it on the robot, right? So it is a long process, but if you do it correctly, you're going to have really good designs that come out of it, really fleshed out designs, and you'll also have, it actually will take less time if you do it properly than if you, try to stumble through every step of the process. So that's what we're going to be getting into today. So the main philosophy of robotics design is that parts make up mechanisms, which make up your entire robot, right? You can see here that we have a part right here. This is a drive base rail. And then here we have our chassis that's made up of 4 drive base rails, right? And then we have our drive base, which is made up of our chassis plus our drivetrain elements such as wheels, motors, and gearboxes. And then we have our full robot, which our drive base is at the base of that. And then we have 2 other mechanisms here, which is our intake and outtake, as well as our climber. This climber allows us to basically do pull-ups, and this intake and outtake allows us to score lemons. If you don't know, what any of that means, that's totally fine. We'll explore it further in the rest of this video. So, right, and you also have to design around the fact that the parts that you're using have to be simple and they have to be purchasable, right? So we have to be able to actually make these, right? So good design is done with manufacturing and construction of your design in mind. All right, so we talked about this a little bit before, but design is task-oriented, right? You start with your task and you move up from there, right? So every part on the robot should have a clear purpose to fulfill that task, right? Whether it's making it stronger or facilitating some sort of rotation, or making something lighter, everything should have a clear purpose. And if it doesn't, it really should be removed because that's redundancy that you don't necessarily need. But usually things will have a purpose. It's very hard to find something that's completely superfluous on a design. So you're going to begin with concepts, right, and compare pros and cons to determine the most effective design. And then this is your major design decisions phase, where you're going to be deciding what you're going to be designing. Then you're going to develop these concepts a bit further using 2D sketches on graph paper. It works really well for that purpose. I usually like to do that. I think graph paper makes me really happy. I don't know if that's a weird fetish, but I really like it. And then next you're going to use your concept drawing to inform the creation of the CAD model for your design, which is you're going to review and analyze that design as you continue to iterate. And that's going to help you come up with a really fleshed out design towards the end. So I've been throwing around this word CAD, right? What is CAD? CAD is short for computer-aided design. Computer-aided design. That's a tool that allows people to share designs with others in a more understandable format. That's literally what CAD does, right? And sharing that design can entail, giving it to somebody so they can tell you what's wrong with it, also known as a design review. And it can also entail giving that to mechanical sub-team so that they can understand it and then make it, right? So ideas should not really be created in CAD, right? CAD is a tool. It's like a pen and paper, and you translate your design into CAD. So you don't make your design in CAD originally, right? You make your design, I don't know, I think of most of mine in the shower, and then I work up from there. But there's some things that you can't see in the shower, so CAD really helps you to analyze and figure those things out as you go. Right, so CAD can also be used to calculate and analyze forces on objects. We don't do that much in robotics, so don't worry about that. But it is useful to be able to calculate strength without having to physically prototype, which saves you money and time. Because, if you're buying parts for prototypes, that's big monies right there. Actually, it's not that big money, but it is money. And, giving the fundraising team the easiest job that they can have is one of your jobs as a designer. There's also many types of CAD software that you can use. Basically, once you know one CAD software, you know them all. I won't say that applies everywhere, but there's definitely nuances, right, like between different CAD softwares. But once you know Onshape, you pretty much know SolidWorks and Inventor and Fusion 360 and many other softwares that are like that. They all operate under the same basic premises, and those work pretty well. So I said Onshape, right? We're going to be using Onshape this year as a CAD software. It's Onshape is a cloud-based CAD software that allows you to run it locally with no downloads, and you can do it that way. So we'll be using Onshape, but other prominent CAD programs include SolidWorks, Inventor, AutoCAD, Fusion 360, and Tinkercad, which is really good. No, I'm kidding. I did most of my learning at the beginning in Tinkercad because it's a really good way to learn parametric modeling. But then, you gotta move up to greener pastures here because Tinkercad, there's only so much you can do with it. Although that so much is actually quite a bit. But yeah, all right, so now let's get to sort of the practical analysis of this activity, which is going to be doing this group activity and sort of giving you guys context. Now, context is key in this program, right? I want you guys to know how to design for robotics. And the first thing we're going to do is analyze our task. So go ahead and watch this video. It will be linked in the description. But go ahead and watch this video, right? And this is the Infinite Recharge game reveal video, which was the 2020 game. Apparently, it's now the 2021 game as well. So it truly is infinite. But yeah, so watch this reveal video, and then we'll analyze the tasks off of that. So you can go ahead and pause the video now in order to do that. Okay, so now that you've come from doing that, let's sort of analyze the tasks that are present in the game. And now there are more if you read the game instruction manual, but the main tasks are all there in the game animation. So, first things first, right? What's our first task? Well, I would say it's traversing the field, right? Driving around is super important because then you can, run into other robots, but you can also, get to the climb hook, and you can also score and other things like that. So driving around is our first task. Second task is scoring. So that entails either shooting into the high goal, shooting lemons into the high goal, or depositing them into the low goal. But scoring is our main task. Those would be two subtasks of that main task, but scoring is our main task, scoring lemons. Our other main task would be picking up lemons, right? And that goes with scoring lemons, but you have to be able to get them onto your robot so that you can use them to score. A next task would be spinning the Wheel of Fortune, like the little, spinning wheel thing, which is a pretty easy task to do. You just need a little wheel to touch it and then spin. But it's also not super important, doesn't give you a lot of points, and it's not super applicable, so many teams just chose not to do it. In fact, many teams who had built a mechanism to do that task didn't actually use it. I think only like 1 or 2 teams in the world actually did that task last year. So yeah, take that with a grain of salt. And then you have your final task, which is climbing. And climbing is super important, right? You have to be able to raise your robot up and lift it onto the climb hook without falling down. So yeah, those are our 5 tasks. 5 tasks, 1, 2, 3, 4, 5. I believe that's 5 tasks, right? So now let's look at the Robonauts reveal video, and this is going to be a mechanical implementation of these tasks I've just described, all right? Of these tasks I've just described. Now we have our first task, which is driving, traversing the field. So go ahead and pause this video now if you haven't already, and watch this video. It will be linked in the description. Okay, now that you've done that, how did the Robonauts accomplish the first task? The Robonauts, they're a very good team, Team 118. They're NASA-sponsored. They're one of the many NASA-sponsored teams, but they are a very, very successful team, and they build really cool mechanisms. So yeah, how did they accomplish driving? All right, well, how they did this is they had a 4-wheel drive tank drive, right? So they had a drive base. And this was just, it's a frame on the bottom of the robot, and they have wheels, and they can spin those wheels using motors, and those wheels are touching the ground, which pushes their robot forward. They have 8 wheels on their drive base, 4 on each side, and they can move each side independently of the other, so they can turn like a tank. Next, we have their intake. How do they intake balls, right? How do they intake lemons? Well, they had this little thing that came down, and it had spinning wheels on it, and as the ball comes up to those spinning wheels grab the ball and lift it up, right? They lift it up into the robot and sort of drop it into the little hopper there. So they had spinning wheels powered by a motor on a little thing that can come down. Next, they have their indexer, which is another mechanism, but it contributes to scoring, right? So basically, their indexer takes balls from their intake to their outtake, which is the last thing or one of their mechanisms there. And this mechanism facilitates scoring, right? It allows them to point at the goal and shoot 5 balls. That's the maximum you can carry, and shoot 5 balls into the goal, right? So the outtake basically works. You've got like a spinning wheel here, and you've got a hood, right? This hood is just a fixed piece of metal, and the ball touches this spinning wheel, and the ball shoots out at the angle that the hood terminates at. There's also another spinning wheel on the end of the hood there. And that allows them to control a lot of things about the flight path of the ball, but most importantly, it just allows them to score, right? So they've got a shooter as their outtake. And then finally, actually not finally, there's 2 more. Then they have their spinner mechanism, which is just to spin the Wheel of Fortune. I think they used it like once or twice in the entire season, but it was admittedly a quite short season. But they have their spinner, which is this belt that they can pop up to spin the wheel, and that allows them to spin the wheel to a certain color. They do have 3 color sensors on that spinner at different locations, so that they can always tell what color they're spinning it to. Probably just have different colored buttons on their driver's station, so that the driver presses a button of a certain color, and Driver presses a button of a certain color, and that's, it works like that, that it just goes to that color. But that spinner can also fold down, that way they can fit under the trench, which would be another subtask of driving or traversing the field, is fitting under the trench, which they do. And also another subtask of traversing the field would be crossing the barriers in the center of the field, which are like bumpy and stuff. So having a robust drive base that can grip well is a really good way to do that. And then finally they have their climber, which basically was like a telescoping nested climber, and they have one of them on each side of the robot, and they extend that climber. There's like a tape measure type thing inside so they can shoot it up and then pull it down, because lowering the climber is what needs to be strong, because you're raising the whole robot when you do that. Extending the climbers upward doesn't really need to be that strong. And those climbers are, right, they're nested continuous climbers, so they're powered by a motor, right, and that motor raises the whole thing up and then pulls it down once it hooks onto the bar. And I don't want to get too into these mechanically, just as a general concept of how this team, which is a pretty successful team, how this team accomplishes the tasks that are listed, right? So their strategy, and this is usually their strategy, is to do everything. But other teams, that don't have as much funding or don't have as much time to do stuff, they can't do everything, right? They can only do some stuff, so strategy decides what stuff you should focus. So our robot this year focused on climbing, which was, we thought it was a very important part of strategy, and that proved to be the case. So we just, didn't make any sacrifices, and we put a really good climber on our robot. And because of that, we were able to do quite well at the competition, even if we weren't able to shoot into the high goal or score in that way. Climbing is very important to us, and that was part of our strategy. Strategy is what wins games. You can't do everything unless you're, the Robonauts. You can't really do everything. And so picking and choosing what to do is super important. All right, so in conclusion, right, think about the end goal. How does design work? You're designing a robot that can do game tasks, that can play the game. So thinking of these different ways to do these game tasks, that's what we'll get into a little bit more in the future. But most of all, right, you have to be able to do the game tasks. And you also have to be able to build the robot. So doing the game tasks and building the robot are the two most important things that you're considering when you're designing. All right, so you have to be able to do the tasks, and you have to be able to build your robot that you have in the CAD. So if you have a robot that can do the tasks in the CAD, it's no use if there's parts in that CAD that you can't buy or that you can't machine realistically, because then it's just useless. You won't actually be able to do them. So you have to be able to design around what you can actually build and manufacture. But yeah, overall, that's just a pretty quick run through of our first lesson. Right? If you have any questions, please post them in the comments below. I would really appreciate it, and I'll try my best to answer. You can also send me an email or a DM if you're on the team. So thank you all so much for watching, and I'll see you all next time.